All right, 11.7 is events involving and, which is conditional probability. So same thing as usual, we're going to go over our definitions first. So if the occurrence of one event has no effect on the probability of another event, the events are said to be independent. They are independent. One does not affect the other. So the probability of A and B will be the probability of A times the probability of B. If they're independent, the probability of A and B is the probability of A plus the probability of B. It's multiplying. A times probability of B. Oh, I'm sorry. Thank you. Probability of A times probability of B. So, for example, if you had a die that you were going to roll and you had the cards to pick, so that's usually what they bring us. So if you roll a die, it's going to have no effect on what card you choose. So these are totally independent. So you do the probability of the first one times the probability of the second one. So the probability of an event occurring at least once is equal to 1 minus the probability that the event does not occur. That the event does not occur. So the probability that it occurs at least once is 1 minus probability that it doesn't occur at all. If the occurrence of one event has an effect on the probability of another, the events are said to be dependent. The events are said to be dependent. So for example, if you choose one card, you take it out and then you choose it, and then you choose another one. You already have one out, so that's going to affect your probability. That's going to affect your probability of the next cards you choose. So it does affect, so these are dependent. So for this case, probability of A and B is the probability of A times the probability of B given A. So talking about or taking two cards from the deck. Whenever I take that first card out, that would be my first probability, times the probability of my new. So, okay, let's do an easier example. If I had 4 donuts, because I'm hungry, 4 donuts. If we had two glazed, a sprinkle, and a chocolate, I don't know. I would take the sprinkle. No. Okay, so like probability of the sprinkle, let's say is 1/4, right? So now I only have 3 donuts left. So now my probability of getting a chocolate would now be 1 out of 3 total. So now because I took that 1 out, I would have a new probability that would affect my next probability. So that's what this B given A is. So after we take A out, what is your new probability of choosing B? We'll do more examples in a second. So, questions? Yeah, please, Emma.
Is it B over A?
It's given. Good question. So it's like, it's a vertical bar. So B given A. So given that A occurred, what's your new probability of B? Thank you, that's a good point. So just a vertical line, B given A. So given that A occurred, what's your new probability of B? So next, the probability of event B, assuming that event A has already occurred. That's what we've been talking about, is given the conditional, is called the conditional. Probability of B given A, and that's what's denoted by probability of B given A. So it's based on the condition that A already happened. It's conditional. So once A happens, take that out, then find your new probability of B. then last but not least, it's the same thing that's going up here. The probability that an event happens at least once can be found by subtracting the probability that the event does not occur from 1. So we said the probability that it occurs at least once is 1 minus the probability that it does not occur at all. So conditional probabilities. You ready for some examples? All right, so it says use a spinner shown. It's equally probable that the pointer will land on any of the 6 regions. If it lands on the borderline, we spin again. So if this pointer is spun twice, find the probability that it will land on blue and then on purple. So we have to find the probability of blue and then purple. Are these independent or dependent? Whenever I land on blue, does that affect how I land on purple? No, just spin again. It doesn't affect. These are independent. Has no effect. So in order to find this, we'll just find the probability of landing on blue times the probability of landing on purple. So probability of landing on blue. How many blue spaces are there? Blue regions. 3 out of how many regions total? 6. Times how many purple regions are there? 2 out of 6 total. We are multiplying fractions, so we're going to multiply straight across. So we get 3 times 2 is 6 over 6 times 6 is 36. How can we reduce 6 over 36? Yeah, they both have a 6 in common, so we can divide out a 6 from the top and the bottom. And we are left over with our final answer of 1/6. Yes, you can also plug it into your calculator of 3 divided by 6 times 2 divided by 6 equals, and then turn this into a fraction. Yes, some of them in my math lab will say rounded decimal, but we'll get to it. All of them so far have just been fractions. And then sometimes it'll want both. Like, so part A will want a fraction, part B will want the decimal. The same answer. Yes. But it's only one problem, so you already have your answer. But yeah. All right, ready for another one? Questions for me? So, use the spinner below. Same thing. It's equally probable that the pointer will land on any one of the 8 regions. If the pointer lands on the borderline, we spin again. If the pointer is spun 3 times, find the probability that it'll land on yellow, and then green, and then blue. So again, are these independent or dependent? Whenever I spin it the first time, does it affect my second or third spin? No, so it's independent. So we're finding the probability of yellow and green and blue. Again, they are independent. Which means one does not affect the other. So just like the previous problem, we'll have the probability of yellow times the probability of green. I'm writing the same thing. Times the probability of landing on blue. So same exact as the previous problem just now, we have three things to multiply together. How many yellow regions are there? 2 out of how many total? 2 out of 8, thank you. Times how many are green? 2 out of 8 total. Lastly, how many are blue? 3 out of 8 total. So multiplying straight across again, or plugging into your calculator, we get 2 over 8 times 2 over 8 times 3 over 8. We get a funky decimal. Changing that decimal into a fraction, we get our final answer of 3 over 128. 3 over 128. How could I help you? What questions do you have for me? You're ready for the next page. All right, so one more spinner problem. So it says, use the spinner shown. It's equally probable that the pointer will land on any one of the 8 regions. If the pointer lands on a borderline, we spin again. If it's spun 3 times, find the probability that it will land on green every single time. So that means if we're spinning it 3 times, we're trying to find the probability of green, and then green, and then green again. So same concept, now we just have 3 of the same color. Independent or dependent? Does one spin affect the other spins? Nope, so it's independent. So that means our formula is the probability of landing on green times the probability of landing on green times the probability of landing on green. What is the probability of landing on green? How many green regions are there? 2 out of how many total? 2 out of 8 total. So same thing, 2 out of 8 times 2 out of 8 times 2 out of 8. Multiplying straight across, we're plugging this into our calculator. We get 2 over 8 times 2 over 8 times 2 over 8. We get the crazy decimal, plugging it into a fraction, we get 1 over 64. Final answer. One over 64. So it's the last spinner problem. Questions for me? Questions for me? If not, let's keep going. So a single die is rolled twice. Find the probability of rolling an odd number the first time and then a number greater than 3 the second time. So we're looking for the probability of odd and the probability of something that's greater than 3. Are these independent or dependent? Does the first roll affect the second roll? No, it doesn't affect it, so they're independent. One does not affect the other. So that means our formula is going to be the probability of rolling an odd number times the probability of rolling a number that's greater than 3. So, if we have a 6-sided die, out of those 6 numbers, how many are odd? 3. So 1, 3, and 5. So 3 are odd out of 6 sides total. 3 are odd out of 6 sides total. So out of our 6-sided die, 1, 2, 3, 4, 5, and 6, how many numbers are greater than 3? 3. So 4, 5, and 6. So we still have 3 over 3. Multiplying straight across or plugging this into our calculator, 3/6 times 3/6 will give us 0.25. Changing this into a fraction, we get 1/4. Final answer. Two more for this page. Of course, you know what I'm going to ask. Questions for me. I just need to have a button that just says it because I feel like I say it over and over. All right, fine. Next one. Use one card. You draw one card from a 52-card deck. Then the card is replaced. And then again, the deck is shuffled. And then you draw again. So find the probability of drawing a 6 each time. So probability of drawing 6 and then probability of drawing a 6 again. So probability of getting 6 and then 6 again. So remember, we're going to take one card out. Once we take that card out, we're going to put it back, shuffle it, and then draw again. So does one drawing of one card affect the drawing of the next card? No, so they're still independent. So because we put them back and shuffle them, it's independent. So one does not affect the other. So just like we've been doing, the probability of getting a 6 times the probability of getting a 6 again. How many 6s are in a deck of cards? 4. So 4 out of 52 cards total. And then again, we'll have 4 6s out of 52 total. because we're going to put that, say if we got a 6, we're putting it back and shuffling it. So we still have all 4. We still have all 52 cards, all 4 6s. Good question. So putting this into our calculator or multiplying straight across, 4 out of 52 times 4 out of 52. Putting this into a fraction, we get our final answer of 1 over 169. One over 169. Last one for this page. Other questions? Last one for this page. A coin is tossed and a die is rolled. So we're doing both. Find the probability of landing on heads and that the number is greater than 5. So we're trying to find the probability of landing on heads and a number that's greater than 5. So getting a 5 on our coin toss and getting heads on our coin toss and getting a number that's greater than 5 on our dice. So, independent or dependent, does one affect the other? No, if I toss the coin, that has no effect on what number I roll. So they're independent. So one does not affect the other. So we're going to do the probability of landing on heads times the probability of rolling a number that's greater than 5. If we toss a coin, what's the probability of landing on heads? 1/2. So we have only one head out of 2 options, heads or tails. On our dice, how many numbers are greater than 5? 1. One number is greater than 5 out of our 6 total. Plugging this into our calculator, multiplying straight across, 1 times 1 is 1. Out of 2 times 6 is 12. 1 over 12 cannot be simplified. Final answer. The probability of the first thing times the probability of the second thing. You ready for the next page? So last page for 11-7. Here we go with the stupid donuts. I knew it was coming. But these aren't as good. I think the sprinkled and the chocolate and glaze are better, but that's me. So Elizabeth bought a box of donuts to share. How nice of her. There are 2 dozen. There's 24 donuts in one box. All are identical in size, shape, and color. 5 are jelly filled. 6 are lemon filled. Who's going to eat these? 13 are custard filled. You randomly select one donut, eat it, of course, and then get another one. Because you can't just have one donut. All right, so find the probability of selecting 2 jelly-filled donuts in a row. So remember, you take one out, you eat it, and then you get another one. So are these independent or dependent? Dependent, because whatever we eat the first one, that affects the next thing. So they're dependent. Which means one does affect the other. So we're finding the probability of selecting 2 jelly-filled donuts. So what's the probability that you get 2 nasty ones? Just kidding. Some people like to. It's like putting fruit in your ice cream. If you're gonna eat ice cream, like you need to put like chocolate and like unhealthy stuff in it. You don't want to do it like healthy and unhealthy. That does not. All right. So, what's the probability of your first jelly? What is it? Sorry. Yeah, so there's 5 jelly filled out of 24 total. Times, just like before, the probability that you get a second jelly-filled donut. So you took one jelly and ate it. So how many jellies are left over? 4. Out of 23. Good, because now you ate one already, so there's only 23 left over. So now you have 4 out of 23. Same concept, multiplying straight across and simplifying, or plug it into your calculator. 5 divided by 24 times 4 out of 23. Changing that decimal into a fraction. Oops. We get 5 out of 138 as our final answer. 5 out of 138. Oh my gosh. Made it worse. I'm a little whiteout happy today. All right, questions for me. A little bit different, but same concept. We're still multiplying our 2 probabilities together, but now the first one affects the second one, so we have to take that into account. Ready for another example like this? Mm-hmm. So probability of getting a jelly-filled donut, and then you get a lemon-filled donut. So we have to find the probability of our first jelly donut. So how many are jelly? 5 out of our total 24 again. So the probability of the second is going to be lemon-filled. How many are lemon? 6 out of how many donuts are there now? 23. Good, you ate one. You probably spit it out. So 5 out of 24 times 6 out of 23 in a fraction will give us 5 out of 92 as our final answer. Out of 92. So one more example. 3 parts, but one more example. Before we go, there are questions for me. Questions, comments, concerns for me? So last one. Express the following probability as a simplified fraction and as a decimal. So this is the one where it does both. So give your action as a fraction and then as a decimal, round to 2 decimal places as needed. So they give us this chart of marital status of certain populations, 18 and older in millions. So we're talking about male and female, married, never married, divorced, widow, and total. So if one person is selected from the population described in the table, find the probability that that one person is not widowed. Not widowed. So we're looking for the probability of not widowed. So if they're not widowed, could mean they're married, never married, or divorced. So instead of going through all those 3 things, it's easier for me to find 1 minus the probability of being widowed. So 1 minus the probability that they were widowed, or are widowed. Are maybe. So 1 minus. In total, how many people were widowed? Are widowed? 8. Good. So 8 widowed people. I don't know if that's politically correct. But... yeah. Out of how many people were total in this chart survey thing? 235. Good. So notice that if we have 3 are male, 5 are female, they already added it up for you. So we have 8 people that are widowed total. So 8 out of 235. So plugging this into our calculator, 1 minus, in parentheses, 8 over 235. 8 over 230. 8 over 235 is its own fraction, so it needs to go in parentheses. We get that crazy decimal, turning it into a fraction. We get our final answer of 227 over 235. So that is our first thing. That's our simplified fraction. Once we find that, it wants you to find the rounded decimal. So 2 parts. So putting this back as a decimal, we get 0.965, blah, blah, blah. We want to round to 2 decimal places. So we're looking for 2 numbers after the decimal. We're going to round this 6. Looking next door is a 5. Remember, if it's 6 or 5. If it's 5 or higher, it rounds up. So it'll be about 0.97. So 0.97 is one answer. 227 divided by 235 is another answer. So both of those are answers. Questions for me? Whenever it says round to 2 decimal places, I want my answer to have 2 numbers after the decimal. Yeah, in the I copied these directions straight from my math lab, and it says do both, so simplified fraction and as a decimal. So make sure you read the directions. Also in my math lab, so thank you for bringing this up, you know, whenever you type in your answer, underneath it in blue, so make sure you read that blue thing, it tells you, put it as a simplified fraction, as a decimal, whatever. So make sure you read that little directions in blue underneath wherever you type in your answer. Other questions? All right, let's do part B. If one person is selected from the population described in the table, find the probability that the person has never married or is divorced. So we're looking for the probability of never married or divorced. Never married or divorced. Are these 2 things mutually exclusive? Can they be both never married and divorced? That doesn't make sense, right? Yes or no. So they are not, I'm sorry, they are mutually exclusive. Cannot happen at the same time. You can't be both never married and divorced. So it means they're mutually exclusive. So that means in order to find mutually exclusive probability, we have to find the probability of never married plus the probability of divorced. Probability of never married plus the probability of divorced. So going to our chart, how many people have never been married? 79. Out of how many people total? 235. Yeah. I was going back and forth to the chart, so it's okay. And let me do just one more thing. So what's the probability of divorced? 28. Out of our total 235. Yes, ma'am.
Would you subtract at the end?
We don't need to subtract because there's not both. They can't both never be married and divorced.
Okay.
But like, say if it was, they could both happen, like the card situation where they could be 3 and black, then we would subtract. So adding these two fractions together, we get 79 added to 35 plus 28 added to 35. We're going to get that decimal. First, changing that decimal into a fraction, we get 107 added to 35. $107 added to 35. That's our first answer. That is our fraction. Turning this fraction back into a decimal so that way I can get my rounded answer. It's about 0.455, blah, blah, blah. Rounding 2 decimal places, we're rounding that first 5, the second number after the decimal. Looking next door is another 5, so it's going to round up and be about 0.46. So those are our 2 answers for that one. Yes, ma'am. Right, because whenever you add, they're like terms, so you just add across the top. Whenever you're multiplying, you multiply straight across. So top times top over bottom times bottom. So whenever you're adding, the denominator stays the same. You have to get a common denominator, LCD. Which here, thankfully, they already had it, so all we had to do was 79 plus 28. Good question, thank you. Other questions? If not, last one. So if a person is selected from the population described in the table, find the probability that the person is female, given that the person is widowed. So the probability of female, given that the person is widowed. Remember, we can write this as probability of female with this vertical line. So given that person is widowed. So this is our conditional probability. For conditional probability, we're going to find the number of people that are female and widowed divided by number of people widowed. And that was our formula from the first page that we talked about. So out of this table, how many people are female? So in this female row, and widowed. So in this widowed column, 5. How many people total are widowed, or were widowed, or whatever? 8. So 5 out of 8. That is simplified, so that would be our simplified fraction answer. And then putting this into our calculator, 5 divided by 8, we get 0.625. Rounding to 2 decimal places, we're rounding that 2. Looking next door is a 5, so it'll round up to about 0.63. So this is the notes for 11.7. Questions for me? 11.7.